Hello, everyone. Today I'm going to talk about our work, which is about from non-cooperative to cooperative interval games using alpha and beta approach. So this is joint work with Zeynep Alparslan-Gök, Elena Parelina, and George Zakor. First, let me start with overall picture. Please just interrupt me whenever you have a question during the talk. Yeah, actually, we can roughly classify game theory in two categories from our work perspective as non-interval games, interval games. Non-interval games are non-classical game theory that you know. Interval games, this is what I'm going to focus on today. So there is a theory of non-cooperative interval game as well as cooperative interval games, but they are not connected. So, but there are also some characteristic functions such as alpha, beta, gamma, delta, but we are having two of them in our work today, which are alpha, beta characteristic function. So from this perspective, these characteristic functions provide connection, let's say as a bridge between non-cooperative and cooperative games. And further, valuable analytical tools to understand how players can collaborate, negotiate, distribute gains in a variety of games. So we thought that it will be interesting to examine how could the cooperative version of an interval non-cooperative games and be constructed. And also, is it possible to adapt alpha and beta approach for the interval games, for the case of interval games? So in the light of these information, our work deals with the intersection of non-cooperative interval games and cooperative interval games, offering novel insights into strategic interactions under uncertainty by introducing the interval alpha beta characteristic function. Let's see. It was our motivation, actually, what I have just mentioned it now. But I want to add one more thing from the general perspective in the interval games. So in interval games, the aim is generalize the classical theory to the interval setting. This is what we are doing now. And I would say this intersection, and by introducing the interval alpha and gamma, this is the main contribution of our work. So, and I'm gonna give briefly some information about intervals so that you can easily follow me what I am supposing to do. So I and J are intervals in the sense that they are just closed and bounded intervals of real numbers. I mean, they are subset of real numbers. So this is the lower bound of I, and this is upper bound of I, and this is length of I, which means upper value minus lower value. So, and this is how you can add two intervals, and this is how you can multiply an interval with a constant. And this is partial subtraction operator, which was introduced by Alparslan-Gök, Brenzi, and Tiges in 2009. So why it is called partial subtraction operator? Because in the literature, the main subtraction operator was introduced by Moore in 1979. So, but in our work, we used partial subtraction operator. As the efficiency of the interval Shapley value that I'm going to use it as a solution method today in our work might be incompleted by using Moore's subtraction operator. If you want to see more detail, you can check the board I showed here, just here. mathematically what is the difference between two subtractions. So, but we will use this subtraction. Another important thing is order relation, because ordering intervals is not an easy thing, actually. So still there are some difficulties on it. So we choose intervals which are partially ordered, which makes a lot of sense, actually. So, for example, to make a decision which interval gives more profit to the player, then you should follow this way. If the lower bound of I is greater than or equal the lower bound of J, and the upper bound of I is greater than or equal upper bound of J, so then you can say I is weakly better than J, so the player should choose I. Okay, and there is also a reverse version of it, which is called weakly less than. So let me illustrate it with a very simple example. Just focus on, please, I and J. So you will see that 2, yes, 2 is greater than -1, and 6 greater than 4. So you can say that J is weakly better than I. And the opposite version is here. But for example, in this case, you cannot say -3 is less than 0. Okay, but 2 is not less than 1. So you cannot say A is weakly less than B. Just I wanted to put as an example to show you. And this is how you can multiply two intervals, and this is division operator, that how you can divide two intervals. Okay, in our work, we consider n-player non-zero-sum interval games defined in a normal form, which is here. So this is an n, the set of players, and each player of I has the set of finite strategies, xi, which is here, and the payoff function of player I, ui, which is interval. And but in particular, if we consider two-player non-zero-sum interval games, which is called bimetric interval game, and can be represented by two matrices, capital A tilde, capital B tilde, and each of whose entries are interval. So the payoffs A tilde ij refer to player 1, and B tilde ij refer to player 2. And then I will say this is the set of mixed strategies for player 1 and player 2 respectively, as you see. And also this is the expected payoff of player 1 and 2, which are interval, as you see here. This is lower bound and upper bound. And now we are on the crucial part of our work, actually. But let me remind alpha and beta characteristic function for non-interval games, as you know. So this is the definition of alpha characteristic function. V alpha S represent the maximum payoff that coalition S can guarantee for itself as independent strategies used by the left-out players. And actually, both of them are constructed under the pessimistic assumption, in the sense that the left-out players form an anti-coalition. So it means that the left-out player whose objective is minimize the payoff of coalition S. So the fact that these approaches are based on a solution of zero-sum games, I will say. And let me introduce the interval alpha characteristic function first, and then beta characteristic function second. Actually, here we extend classical case, well-known alpha and beta characteristic function to the interval setting. So here the definition, and it is shown W alpha, and here the utility is payoff function, which is US. This is lower bound of US, and this is upper bound of US, and they are calculated as follows. This is how we can calculate the expected payoff in classical case. So you can see, I mean, you can follow. And this is another definition I would like to introduce. The interval beta characteristic function. As you see, only the difference, I mean, min max, max min. So, and let's move to the next step, which is an algorithm for n player. So if you consider only 2 and 3 players, then it's okay. You can compute the interval alpha characteristic function and beta as well. But if there are n players, then you need an algorithm. So this is the algorithm what we need for n player. Okay, I put the algorithm here for alpha characteristic function, but we have the same recipe for beta as well. So first step, choose a collision, and second step, what you choose for, build a payoff matrix for collision S being player 1, and then you can compute the max min value at the third step. How we can the procedure of finding max min value, I'm going to show you later on while giving an example. But for more detail, you can check Lee's paper. And before the last step, set the value of alpha characteristic function that we obtained in the previous step. Here it is. And then read those steps for all collision possible. So let me give an example for this to make it more clear in your mind. Here is an example with 3 players. Let me explain how the algorithm works. So here we have 3 players, and any player has 2 strategies. And x1, x2 are strategies of player 1, who is row player. And y1, y2 are strategies of player 2, who is column player. And z1, z2 and are strategies of player 3, and who is matrix player. So, for example, when player 1 and 3 form a collision, by the way, you know, but I just mention it again. So first payoff refers to player 1, right? The second payoff, which is pink, refers to player 2, and the third one, which is orange, refers to player 3. So when player 1 and 3 form a collision, then we summarize these 2 intervals against the player 1 as being player against the collision 1 as being player 1. Or for example, when player 1 and player 3 form a collision, then we summarize these 2 intervals, and then you can follow the steps that we know in the for algorithm. Okay, let me start to solve it. So we start with collision 1 as being player 1, and the left out player, which is n minus s, as being player 2. So while solving this problem, what I am doing is this. For example, when you have a collision S and also a collision, the left out collision, the left out player, which is n minus s, will be there, right? So I'm going to compute both of them together by following all the steps. Okay, so here, as you see, we summarize these two intervals. Yeah, and then this is the payoff matrix that we get it. And please just focus on blue entries, because we build a payoff matrix for collision S being player one. So this is the payoff matrix that we need. And here, I'm going to compute the max min value, how we can compute it on the first row among these intervals. I think it's not very difficult to see. This is the minimum value, right? 0, 0, 2. And on the second row, among this interval, this is the minimum value, 3, 6. And among these two minimum value is maximum value is 3, 6. So this is the max min value that we get it here. And also the same, following the same procedure, you can also find a min max value, which is also, in our example, in this collision, which is also the same with max min, but it's okay. So similarly, compute the max min and min max value for collision 2, 3. This is the payoff belongs to this collision, and when we follow the same way, we will get these answers. And before the last step, set the value of alpha and beta, because I also compute beta, right? So all the values are here, as you see. And for example, if S is equal N, which is grand collision, then it means that all players form a collision together. Then we need to summarize all payoff, and which is here. But among these intervals, just we need to find a maximum value. And also, at the end of the algorithm, we will get the grand collision, and which is 1729. Yeah, okay. And last step, read those steps for all collision possible. As I said before, the results are given in the table, that I'm gonna give more detail about this table later on. But you can see all of all of the values in this table. And okay, let me move the cooperative part of our game, our work. Until that point, we considered non-cooperative interval game. But now, what we are gonna do here is this. Actually, cooperative interval games, the fact they are extension of cooperative games. So, and they are useful tools for modeling various economic and war situations. And most of problems that worked in this topic in this area comes from real life situations. So, and here, I just remind you, this is the value of collision S, which is interval, but suppose that the lower bound and upper bound are equal, then it is called degenerate interval and corresponds to the classical cooperative game, because it is no longer interval. So, 1 point. So it calls degenerate intervals. And here I will say the game given by W alpha or W beta that we are working on it are size monotonic. Actually, at the beginning, I mentioned it, why we are using this subtraction because of efficiency condition. And the interval Shapley value is defined only for subclass of interval cooperative games, which is called size monotonic games. This is also, we are working on this class. And the game we are working on also is supermodular, but it is not convex. So why it is not convex? Because of second condition. Normally, in classical case, for convexity, you need only one condition. But in interval setting, we need one more condition, which is here, which is about length of collision. So second condition does not yield. So that's why it is not convex. And I will also show you while giving an example more clear. And now in cooperative interval game, there are various interval solutions, but I'm gonna focus on two notable ones, which is interval Shapley value and interval core. So this is the definition of Shapley value. Actually here, we can also write like this, more clear. Now I will use the same example that we used before, and I will use this table while calculating interval Shapley value for 3 players. And this is the calculation for the interval Shapley values. Here, for player 1, for player 2, and for player 3. Please note that the sum of these components are equal grand collision, which is 1729. So the efficiency is efficiency yield. So let me calculate also interval core, but I mean, before that, we can also compute the interval Shapley value by using beta characteristic function. So this is the result. This is the value of interval Shapley value for 3 players. And we can summarize these values in this table. And I'm gonna give more detail as well at the end about this table. And let me calculate interval core. This is the definition of interval core. First one is efficiency condition, and second one is stability condition. And again, we will use this table. So to solve, okay, we compute interval core just considering 2 linear programming problems by using lower bounds and upper bounds, writing separately, just as you see here. So solving these linear programming problems give us an element of core, not the core itself. So when I compute these problems, and you will get, for example, for W alpha, the interval payoff vector will be this. And this interval payoff vector is element of core W alpha. And similarly, we can find it for beta, which is here. This interval vector is element of core W beta. So we can also compare some other interval vector which is not element of core. We can also easily see.
So here we are generating only one element.
This to solve this problem, yes, give us an element, yes.
So the usual trick of writing all inequalities to determine the payoff of each player between the lower bound and upper bound is not working here.
This is what I did.
Yeah, but I mean, why you cannot say for is the set of this instead of exhibiting only one
But I mean, okay. But you mean this is also here? What I get from by solving lower bound here, and then at the end of the solving, we put like this. For example, when I solve the just lower bound of this problem, I get it.
This I understand, but you are not able to write CW alpha is the set of this and that.
No. Because we are looking for extreme point of polytope.
Yes.
So.
Okay.
Yeah. And here in this part, we come up with some key observation. What we observed here is this. Let me first focus on core. When comparing these two cores, I mean element of core, we conclude that player 1 and 3 prefer alpha because these two intervals is weakly better than these two intervals. But player 1 prefer beta as we focus on these two cores because 3-5 is weakly better than 1-5. But if we consider two Shapley value that we obtained in the previous example, and then we conclude that player 1 and 3 prefer alpha characteristic function. You can follow here again because these intervals weakly better than these intervals. So if he has a choice, of course he should choose this. But player 2, different case, because here beta characteristic function, this value is weakly better than this value. And if we go back and focus in this table at the start of our example, then you will realize that for any collision, the W beta value is weakly better than W alpha. Here you can follow all of it. But if the S is equal N, which is grand collision, then this is the certain thing that wall of value will be the same for every time. Yeah. And so this is what I mentioned it before. W alpha, the game given by W alpha is not convex because of second condition. Just I wanted to write here, the length of W alpha of collision 1 plus W alpha, the length of W alpha of collision 2, which is 5, it should have been less than or equal, but this is not. So 5 is greater than 4. And in this case, the second condition does not yield. So that's why it is not convex. Yeah, but anyways, a supermodular interval game is not necessarily convex. So just these things were our observations.
This is really a big difference with usual games.
Sorry?
This is a very different result with normal games. Let's say.
Of course. Yeah. In the interval case, exactly different. Yeah. So in a nutshell, I would say our analysis shows that different approach yield different characteristic functions for interval games, and consequently a different cooperative interval solution, because these are very important for provide a bridge between non-cooperative interval games and cooperative interval games. Yeah, that's all. Thank you so much for listening, for attending.